So what we will do today, we will continue our discussion on these spherically symmetric potentials, and we'll do the final example of that, which is the famous example of particle in a Coulomb potential, and solve the associated problem of discuss about the associated problem of hydrogen atom. And again, we already discussed all the kind of problem which one can do in this spherically symmetric class of potentials. And this is the final class which has a special some special properties. So let's first discuss the special property. So we already talked about that what happens when this quantity RVR RVR tends to 0 in the R going to infinity limit. We saw that that kind of problem will admit two kind of solutions. One is for bound state, which will of course exponentially decay at R going to infinity. So if I plot like R going to infinity here, it will exponentially decay, and it must go to 0 at the origin. So then whatever something else can happen in between. Or if it could be a scattering state in which it will continue to oscillate at R going to infinity, and it must be 0 at R going to 0, and again something else can happen. But these are the condition when RVR is going to 0 in the R going to infinity limit. But then there is of course another very interesting class of problem where this doesn't go to 0 at R going to infinity limit, and the most famous example is Coulomb potential or anything slower than that. So let's say some even oscillator like simple harmonic oscillator, of course it doesn't in these kind of cases you cannot of course immediately predict that what is the going to be the structure of the solution. But and we already saw in great detail the oscillator problem. So here we will talk about what happens in the class when RVR tends to 1 in R going to infinity limit. So let's first discuss the solution intuitively, like the way we did before. Take the limiting condition and try to put some physical argument and try to visualize the solution, and then of course finally we'll do the full formal mathematical solution. So again, let's first look at the E greater than 0 solution, which is the scattering state solution, and that will be the so in this case, let's recap once quickly what happens in this, what you did in this case. We put the R going to infinity limit RVR to be 0. So if the VR even itself goes to 0, not just RVR, so then this will be the form of the equation, the U equation. Nothing will depend on L. As you can see, this equation has no L here, so I am dropping the L term. So E greater than 0, we saw this is oscillatory with this K form, and E less than 0, it is the bound state exponential form. So now you might wonder that why am I talking about just RVR going to 0, not just VR itself going to 0. So that is a more general condition, and we will see that condition is more it encompasses a more wide class of potentials. So let's take the general scenario when and discuss the case when E is greater than 0, which is the oscillatory solution. So we are talking about right now E greater than 0. So then the UE for in general will be of this form. It is not necessarily of the form a constant e to the power plus minus I k. I mean, it could be a constant at R going to infinity, but somewhere intermediate it could admit a R dependent prefactor. So that doesn't matter as long as this part is there. So let's try to see what kind of condition FR must satisfy in order this to be constant at R going to infinity limit. So that is what I expect that to be in the R going to infinity limit. So let's look at the radial Schrodinger equation, which is this, and plug in this answered solution. So this answered solution will give me a condition on the F, which is F double prime plus minus 2ik prime minus 2 mu vur by h bar square F equal to 0. And we expect that Fr to be at least slowly varying as R going to infinity, even if it is not becoming constant. So then we put a and if it is not slowly varying, then that will dominate the behavior, and you will not get the essentially the oscillating behavior. So that part will become the more dominating behavior. So if it is slowly varying, I can ignore the F double prime. So that means this equation can be written in this form, and the solution will take this form. So general solution Fr is some Fr naught. So you put like it's a first order differential equation. So you have one boundary condition, and that is given by the Fr naught exponential minus plus I mu by k h cut square R naught to R integrating Vr prime here. So now you can see that if now the RVR goes to 0 as R going to infinity, we can take the R going to infinity in this. So we can see that by taking this R to be infinity in this integral and want to see what happens to this FR in the full space. So then this integrand, when you work out this integral, this is an object of order RVR. So this whole thing is an order RVR object as the R going to infinity limit. So then this must remain finite, or this must go towards 0, and then only you can get and if it, at least if it goes to 0, then you get the FR to be a constant as R going to infinity, because then this whole thing will be 0, and then what FR will become, it will become FR naught, and then you recover the original ansatz which you worked earlier, which is a e to the power R plus minus I k r. So that's what tells you that why you need this RVR to the generic condition of RVR being going to 0, not just VR itself. Okay, so now what happens in case if that is not true? So if, so let's say this RVR is not going to 0, so this integral is of order RVR, and this guy is not going to 0 at infinity. Let's say it is not going to 0, then it's going to some constant, which happens again for this kind of potential, which is VR of order minus R square by R. So did I make a typo here? No, I think it is fine. So so then I plug in this 1 by R form. So this 1 by R form here. So then what I'll get? Yeah, I think I made a typo. So this must be E square. So because I wanted to do this new so hydrogen atom like structure. So this is E plus E and this is minus E. So there is just one proton. So that's why it's minus E square by R. So now if I plug in this, so then it will become this is a 1 by R dr integral in this limit. So it will become log R by R naught. So this is the solution I must expect at R going to infinity. So if I plug that this form, I'll get this plus minus I k r plus mu e square by kh per square a log R by R naught. And this is the interesting structure of this problem, that no matter how far you are away from the potential, your solution will always contain the potential itself, which means it will or it will always contain the information about the potential itself, because this integral didn't this guy didn't vanish, and this kappa will contain the energy, and the fact that you have this e square minus r potential, that thing is hidden inside this structure. So that is the so the even if you're at R going to infinity, the potential will continue to influence the solution. Will be it might be very negligible because it's an exponentially decay form, but it will continue to influence the solution, which is not the case for the potential if RBR goes to 0. Okay, so that is a very special property of this kind of potentials, where RVR goes to constant at R going to infinity limit. And this is not only just for RVR being constant, it could be for any VR which is slower than R. That means it decays, but so it decays slower than R. So it could also grow, or like it could be a form like log R or something like that. So now that we got this solution form, and this is actually, you can see this is actually a power law. So let's look at it once more, at one more level of detail. So first we consider this. So this is actually a power law because this exponential and log is there. So when you take this term separately, it will become a r by r naught to the power this object. So that's why it's a power law. So now let's look at the bound state of solution of this problem. The bound state is actually very easy to get, because as we know that if we just change the k to I kappa, where kappa is this, so bound state is just E greater than 0. So if you flip the sign of the E, you will get this, and then you are taking square root, so you get an additional I. You can just replace the previous solution and place k by I kappa. So then you get this decaying solution and growing solution, and the growing solution will go to 0 because the B part will be 0, because of course R going to infinity limit, you cannot the wave function to blow up. So the only states which are there are basically this A to the power minus kappa R. And also notice this only matters because it's a bound state, and when we'll do a formal solution, we'll of course see not all energies are allowed, only certain energies are allowed. It's a quantized state, and only on that case this matters, that this part is there and this part is not there, and you don't need to even worry about the other part of the solution at all. So there will be this allowed energy state solution and not disallowed energy state solution, because it's a bound state problem. So then in the Coulomb case, so again if I take this guy and replace k by kappa, I'll get this form of the solution, and this is basically exponential of a log. So it is a power law, and it will come to be this form. So this is what I expect in the r going to infinity limit, the solution to be of this form. So this will, when we'll do the formal solution in few minutes, you will see that this will be indeed the form which you'll get by doing the full series solution, and you will use this structure, that this guess that what must be the form of the solution in the r going to infinity and r going to 0 limit. Okay, so now this intuitive part is actually very important. So this is, I want you to go through this on your own very carefully, and because as I was saying that this whole solution is kind of complicated, you should do it once, but you won't often encounter it, and unless you are often encountering, you will obviously forget it. But the part which you should not forget or is this part, which is this intuitive part, because it doesn't have a lot of complicated mathematics. It's just a just basic common sense of what the solution must take the form at r going to 0 and infinity, this kind of limiting conditions. And this is actually a very important thing to skill to acquire by itself, because often when you solve a problem you don't know the answer is right or wrong. These are the kind of consistency checks you should do, like put r going to 0 limit, put r going to infinity limit, see if the solution is making sense, if anything going unphysical, and if it is something weird is happening, can you explain that? So that is the kind of thing you must keep doing for any problems. Okay, so now I will go to the full problem, which is the hydrogen atom problem. So this problem is basically a very simple model, like the early models of atom was that there is a particle, a nucleus is sitting at the center. It's just like the solar planetary model. So it's like a heavy particle is sitting at the center and a light particle is orbiting around it. So that's the electron is the small. So in for hydrogen atom it is just a single proton, but for a heavier atom it is like multiple protons, and if by electromagnetic interaction only talks between the charge. So if the atomic number is z, so there are z protons, so Zd is the charge of the nucleus, which is of mass m, and the electron has mass small m, and that is of charge negative charge e. So if that is the case, your potential will be of the form minus Zd square by r. For hydrogen atom, Z is equal to 1, and you know that because there is a single electron and single proton in hydrogen atom, the ratio between these two mass is order of 1 by 2000. So that means you can safely assume that if you go to the center of mass coordinate, normally you have solved this kind of two-body problems in classical mechanics. You know that the right way to talk about is not like a particle is orbiting around another particle, is rather to say that the both of the particles are orbiting around their center of mass, and the center of mass is almost here when the ratio is like too high. So you have done this kind of two-body problems in classical mechanics, right? The center of mass coordinate, lab coordinate, and all this. Hello, am I connected?
We haven't done that lab coordinates yet, sir.
But
In
you have
this
done
scattering
center of
problem.
mass?
Center force, yeah, like we are doing central force, but we haven't come across the part where they talk about the laboratory conditions in scattering cases.
Yeah, so but you will do that eventually, right?
I hope so,
Okay.
but like that was the part of the syllabus, but due to the constraint of time, we don't know yet.
Okay. So yeah, so it is basically a very simple picture that if I have these two particles, so their center of mass must be located at some. So if I have their coordinate is r1 and r2, so you can write the center of mass to be at location. What is that formula? m by m plus m, something like that. So let me see if I have it written somewhere. So I was looking at this. Some book has it in great detail. Okay, I have to look it up. I forgot the formula exactly. But the physical picture is following. The physical picture is there are this there is a common center of mass between these two a small object two object, and it is not exactly this guy is rotating this guy, but they are basically rotating orbiting around this center of mass. So that is what you see from the lab frame. But if you are from this, of course, if you are in this particle, you will see this guy rotating around you, and if you are on this particle, you will see this guy rotating around you. But if this mass is almost here, like if these particles have mass ratio of 2 skewed, then this object is almost here. So then you can safely assume, even in lab scale, that this guy is almost static and this other guy is moving around it. So this thing is called actually Born approximation, and this is not always true. This is not always true for heavy nuclei and heavy atoms. So there is a great deal of work in chemistry and all that, so where this Born approximation has to be carefully handled, and we will learn some more about it in quantum mechanics too. But right now we just assume that the heavy nucleus is static and the electron is just moving around it. It's just like a planetary kind of model, very simplistic model. And this turns out this model is almost accurate, almost accurately gives you all the spectral energies which are experimentally verifiable. So let's see the solution of this problem. So I start with the hydrogen atom, the radial Schrodinger equation, and we know that it's the radial part is the only part which we have to solve, because the angular part doesn't have a potential, and that because the Vr is a central potential, a central force. So it doesn't matter what the angular part is. The angular part is just the ylm theta phi, because of the symmetry of the problem, and that we already worked out earlier. So now notice I will do some dimensional change, which is something we did also in the harmonic oscillator problem, to make the problem coordinates dimension free, and that will be aesthetically pleasing and easier to deal with these equations, and also very helpful to compare with physical scenarios. So let's do the dimensional change. So what I'll do, there are only dimension full quantity here are z, important dimensional full quantities are z and r in the operator, and this sorry, e and r, e is the energy and r is the distance. So I will introduce a scaling physical constant which is called the Bohr radius. So Bohr radius was basically a quantity which in the original old quantum theory, Bohr quantization quantum theory, was used to estimate the distance of the or radius of the orbit, which is the smallest energy orbit. So that was a naught equal to h cut square by m square, which is also something we will get from here, but that's where this a naught came from originally. So then I scale this. So I take this a naught to be the distance of unit, unit of distance, and then r is basically a naught x. So x is a unit free coordinate. But instead, I will do a little more transformation. I will instead call r as a naught by 2z. So that is just to take the z away from the equation. This z is a constant hanging at there, and that for hydrogen atom problem I also don't even need that, because the z is 1 in that case. And the 2, I use the 2 here because just to get rid of some extra 2 hanging out here and here. So that is why I took this 2 here. So if I now put these things here, so then in the x coordinate, the equation of motion, the Schrodinger equation will become this, and this side I will get the E by 2z E square by a naught, which is a little weird expression of the energy, which I simplify by calling it kappa square. So kappa square is minus E by 2z E square by a naught, where this is of course greater than 0 because the E is less than 0 for the bound state solution. So then my full equation is basically minus d2 dx2 minus plus L into L plus 1 by x square minus 1 by x on this side, which is the full operator, and this is on this side you get the kappa square. So this is basically my transform stationary state Schrodinger equation which I must solve. So now there are some more simplification we can do, because we already discussed that in the x going to infinity limit. So now x is my new distance of an new distance in the unit free coordinate, unit free scale. So in x going to infinity limit, this equation will become just this is just u double prime equal to kappa square u. So this has this exponentially decaying solution, which is of course what I expect from a bound state. And I want to, this also tells you that I can have another level of simplification by just taking, so these both of these are unit free, so then I can just call it a new dimensionless quantity called rho, which is kappa x. This is just another level of simplification, and we'll see that will help us, like the cleaner looking equation is much easier to deal with some h and am and this and these handling here and there. So there is a high chance you will make a mistake in the intermediate step of the calculation. At the end, your result will be very hard to untangle that where did you made the mistake after you got the result. So it's better to work with a very clean looking equation which doesn't have hanging e squared, z, and factor of 2 here and there. So what you all you have to do is, after you get the solution, you have to do these reverse transformations, this reverse transformation, to get back the actual expressions. But in between the lines of the calculation, this is very important that you try to make your equation as clean looking as possible. So that is a generic advice when you do any problem. And this is a very clean looking equation with minimum amount of random 2, and so most of the time the mistakes happen in calculation is factor of 2 and minus signs, and of course square, cube, all those things. So those things are not there in this equation, so it's much easier to handle. But this equation is not yet very good, a very good equation for a series solution, because you can see there are three terms. So there are three terms are like this. So this is a second order derivative term, so it's one will give you two order less. This is a divided by rho square term, divided by rho term, and there you have a no power term. So then this three term solution will not so there will be like three terms related between each other. That recursion relation will not be easy to solve, and you will need another like equation after that. So what to do? So now we have to put a little more, we have to massage this equation a little more to get it in a more reasonable form. And for that I will put a answered solution by using what happens at rho going to infinity and rho going to 0. So obviously you know what happens at rho going to infinity. So you know that at rho going to infinity this thing has to be of this form, and rho going to 0 this must be of this form, which you obviously know by this kind of by this exercise, that it must have this power law form. But how do you know that it must be of this rho to the power l plus 1 form? That you can see very easily, that if you put the rho going to 0 limit, the term which will be the most dominating term is this term. So you will get a equation which is u double prime equal to rho square l plus 1, and that will have a solution of this form, which is rho to the power l plus 1. So now if these two limits are settled, so then I can put my answered solution u to be of this form, rho to the power l plus 1 and u to the power minus rho. So you know obviously at rho going to 0 limit, this term is going to dominate and this term will vanish, and rho going to infinity limit, so this overall behavior will be of this form, u to the power minus rho form. Okay, so now with this answered solution, so now I plug in this into this equation. So now my only unknown factor is w rho, which I want to know what is the form of the equation at intermediate rho. So now if I plug in that, I'll get an equation of this form, which is rho w double prime, which is second derivative of w with respect to rho, plus 2 l plus 1 minus rho w prime, which is dw d rho, 1 by kappa minus 2 into L plus 1 W. So this is the form we get. It might appear that after all this this was such a nice looking equation, and you did transformation and made it more difficult looking. But the good thing about this equation is that it has all this second derivative with a rho factor, first derivative with a rho factor, and then there is no derivative. So that means there will be just two types of terms. When you do a series solution, you will just get two types of terms, and that they will give a simple recursion relation. So if I now use the series solution, so I plug in this, and I compared the terms of identical order, I will get a relation like that. So AK plus 1 to AK. If you would have tried that into this equation, you would have gotten a relation which involves AK plus 2 AK and AK plus 1. So that's why it's much more difficult to handle. So this massaging allows you to get just two unknowns and their ratio. So this is the ratio you will get. And again, for obvious reasons, so did somebody message me? Am I connected? Yeah, I think so. Okay, am I connected?
Yes, sir.
Okay, so I got some message. I thought in case I'm not. Okay, so now I put this recursion relation. And then notice that as earlier we know that this recursion relation must terminate somewhere, because if it doesn't terminate, it won't be a normalizable solution. And the termination condition will be given by, so this must be a polynomial form. So there will be a certain n for which the n plus 1 is 0. So that's the termination condition. We earlier found that. And this will give me the quantization of energy. So that tells me when that happens is basically when the numerator is 0. So the numerator 0 is in the limit in the case of 1 by kappa is equal to 2n into n plus l plus 1, when n is the particular integer at which this numerator vanishes. So now that tells me that so this kappa is of course has the energy into it. So then this solution is n. So this is just a convenience that I call this whole thing is an integer. So I call it n. And for historical reason, this n, because this n, the energy value I will get is in terms of this n, because that is what Bohr got by using his conjecture of quantization of momentum, quantization of angular momentum. And for that reason, this thing is called the principal quantum number, and that will give the full n solution. So that tells me that this small n must be equal to n plus l plus 1. And this n can be so the lowest value of n and l can be of course 0. So if both of these are 0, the n must be 1. And if sorry, just a moment, I'm just getting a call. Just a moment. Okay, I'm back. Am I audible? And my screen is visible?
Yes, sir.
Okay. So now this tells me if my n and l are 0, both of them are 0. So this thing is this total n can be 1 because of this 1. And then similarly it is 0 1, so then it is 2. If it is 0 2, it is 3. And similarly for 1 it could be 0, and so on. And all these possible combinations of n and l's are there, which says that the total sum is invariant. And that gives me this n equal to 1 2 3, all the possibilities. It starts from 1 and then it can go to infinity, and for that n and l could be this. So then my total energy can be expressed in terms of, so now I revert back to the original energy unit. So now this kappa square, of course the E is of this form. So then if I put these integers, so En becomes of this form. So that is the energies of this possible energies of this hydrogen atom problem. And as we know, this is also the energy you get by doing the Bohr by the Bohr condition. So that was of course a remarkable empirical thought of Bohr. So who of course looked at the experimental result and conjectured a particular quantization condition which will give these quantized energies. But at that time they didn't know that what is the reason that why it is like that. So this wave function and all this business, that was the old quantum theory, of course didn't know that. But the formula was correct. So when one did this full Schrodinger equation and the full machinery calculation, one is expected to match that formula, and this is the formula you get. And this is the spectroscopic En which you get from experiment and also Bohr quantization. So if you put in the numbers, the electron charge and the A0, the Bohr radius and everything, and convert it into electron volt unit, you will get this set of numbers. So that gives you a very precise, predictable, and checkable quantity. That if you look at the energy levels of a hydrogen atom, they must be 1 by n square, some integer square, times minus 13.6 electron volt. Very precise number which one can measure experimentally, and that's what one people did and found this to be very accurate. So I mean, not fully accurate because there are some approximation, some missing thing here and there, but it's fairly accurate, which will account those mismatches later. But at least up to the experimental resolution of that time, this was a very successful prediction. Okay, so now we worked out the energy levels. So now I want to work out the wave functions. So the wave functions of this, so this is my equation to be solved. So I want to know what is this W polynomials. So this is again, this is a kind of equation which we have already seen earlier. And these solutions are called associated Legur polynomials. So this is again a polynomial. So just like a harmonic oscillator, you saw these Legendre polynomials, and in this Legur, some form of this uh, Legur polynomial you have seen earlier in other central potential problem. So here you will get these polynomials which are called associated Legur polynomials, which has this kind of a recursion relation or a generating function. So just like again Legendre polynomial, you can write down the kth order. So there are these two orders associated with, there are two integers which are n and l. And for convenience, I am writing it in this form of 2l plus 1 and n minus. So this guy is basically the n, the capital N. No, am I right? So this is, yeah, this is the capital N. So n minus l minus 1. So this is the convenient form to write this down. And this function takes, so if you know the function LP0, from there you can construct this solution. And LP0 for p equal to 0, of course, if you put the p equal to 0, it becomes just the derivative of, it is just 1 basically. So that is how you get this whole solution. Not 1, sorry, it is e to the power x, because this is no derivative if at p equal to 0. Okay, so now if you get, if you work out this form, so now you can write down the full wave function. The full wave function will of course have the radial part plus the times the angular part. So it will become some normalization constant which you need to integrate to show that the psi n l m square dr, so r squared dr d theta d phi, so r going to 0 to infinity and theta and phi going to 0 to pi and 0 to 2 pi must be equal to 1. So this condition, satisfying this condition, will give you this normalization condition. So you will get this normalization condition times this radial solution, which is of the form UNL by R, and the angular solution which we did earlier. So this part is in the rho coordinate. This is rho to the power L plus 1 e to the power minus rho times the W rho NL, which W rho you get by solving this equation, and that is of this associated Legur polynomial, times this YLM theta phi. So this is your full solution. So now if I write it in a little cleaner looking form, it will become the normalization condition times this one, and rho will cut. So this is rho to the power L e to the power minus rho. This is a polynomial of degree n, but the n is given by n minus L plus 1. So that's why I'm writing it as n and L. So these are anyway solution of a equation which contains both which contains a L, and the n comes from the fact that this solution must be a polynomial form such that it is normalizable, and because it's a bound state solution, and this YLM is the angular part. So then I go to the R coordinate, which is where the coordinate where I want to look this solution at. So it becomes psi NLM R theta phi becomes n times R by a naught e to the power minus zr by n a naught. So this I'm converting this into R coordinate. Then this guy is a polynomial in R by a naught of degree n, where n is capital N is small n minus L plus 1, and this small n is the principal quantum number, and this L is historically it is called azimuthal quantum number, and this angular part is YLM theta phi. So that is your full solution of this differential equation. Now I can just write down a few of these forms. because this n I have not yet worked out because it's a nasty integral when you do the full problem, but it's a very simple integral when you look up at the simple wave functions. So if I look at the wave function, for example, 1 0 0, so n equal to 1, l equal to 0, m equal to 0, it will take this form. So 200 will take this form. So if this normalization worked out by solving this integral, of course. Similarly, 210 will take this form, and 21 plus minus 1 will this form, and so on. So this is instructive to once look into that, and I will show you some of this wave function in some I googled this. So if you Google it, you will find the plots of this, which is something useful to do just to see that how these things actually look like. So let me share my screen for that. Where did that go? Your entire screen. Okay, so can you see the web page I'm showing you?
Yes, sir.
Yes, sir.
Okay, so this is a very instructive thing to do because this will give you these solutions. This is this website called Hyperphysics. So if you go to this website, they will give you these solutions. And so this N1, L, and ML to be 0. This is historically, these things are, so spectroscopic people call them S orbital. So this L is called S orbital. L equal to 0 is called S orbital. L equal to 1 is called P orbital. And L equal to 2 is called D orbital. L equal to 3 is called F orbital. So similarly, like they keep name this, and the naming doesn't have a very sequential structure, like it is not ABCD, it is just SPDF, like that. So if you look at this solution, this 1S, so this is 1 and this is S, so that is why the spectroscopy people refer to it. And when these notations were introduced, that time this ML and all these things were initially not, the spectroscopic resolution and etc. was not very good enough to detect those, and people even didn't know about, because these are degenerate levels, unless you have some spin quantum number and all those things. So people didn't name this after this. These are like old nomenclature. And when you do spectroscopy, or like you will take a course on atomic and molecular physics, you will find there is a much better nomenclature. These are called term factor nomenclature, and that will give a later, a combination of letter and number will very precisely tell you the entire state. It's easy to remember, easy to communicate, and you can construct the whole state from that symbol. But right now we will just use this NLM notation. So then this full solution is of this form, the RR form. 200 is this form, and so on. So this is the radial part. And so this is, so combined give you the, okay, combined gives you the theta, also the theta and phi part. So n equal to 3, they give you all these forms. So illustration, if you look for illustration, they will plot the wave functions. So let me plot some simpler ones before I look at the complicated one. So if I plot the 1s, so that tells you, so this is the distance from the origin. So this tell you the 1s has the highest probability to be very close to the close to the origin. And if you plot them in 3D, so the 3D plot is not so uh, easily done here. So for that, I suggest you to go to this Wikimedia page, and it is actually a student project or something like that. Some student only did that. And the good thing is that they also give you the code of this. So if you can look at the source code for that, how to construct it. It's a Python code with some C component, transferred C component. So you can just copy that code and run it, or you can just look at it here. So the n, so this solution is of course a fully symmetric solution. So if you look at this, so they did a 3/4 slice of the solution, and they did a half slice of the solution. This is how the n equal to 1 solution looks like. The n equal to 2 solution, of course, it has, it will not look, if you slice the solution, you will find another region, a shell-like region in the middle. Similarly, n equal to 2, l equal to 1, m going to minus, so minus 1, 0, and plus 1. They will have these three structure. Oops, I did some. They will have this kind of a structure. and so on. Like n equal to 3 will have some structure like this, n equal to 3 will have this structure. So this is the probability cloud will look like this. So at the origin is the nucleus is sitting somewhere at the origin, at the center, and the probability cloud will look like this. And there will be always a so if you look at this plot radially, like just at the radial direction, you will find them to have this structure. So for example, this if you look at this, let me see if I can show you another form. Most probable radius. Yeah, so let me look at this 2s. So you can see that 2s has two peaks. Okay, so the 2s has two peaks, and that is that you can see from here by saying that the 2 and s will have these two regions, like these two regions at the center and at the edge. Similarly, if you have something with three peaks or something, you will get that accordingly. You will get that form. So that is basically the whole game. You can look at the and so if you want to visualize it, you can think that the nucleus is sitting somewhere at the origin. Like if I take this picture, the nucleus is sitting somewhere at the origin, and then the wave function has a finite probability of being here. Of course, the probability is non-zero but negligibly zero everywhere else. Like even it can be, there is a finite probability of leaving it at very far away, but even that is negligibly zero, exponentially suppressed. And more higher and higher orbital you will get more and more fancy and funny structures, and they will have their particular symmetries. So for example, you should be able to, so if I look at a particular L equal to 3, the m, for example, the m ones given a particular m equal to -3, -2, 1, they will all have this z symmetry. So if you rotate the z axis, and that is what you know because you got them by Lz being constant. So that is the kind of thing to observe for this kind of solution. And of course, if you look at two different solutions, you won't obviously find the same symmetry. So for example, if I look at the solution at n equal to some arbitrary n and arbitrary m, you won't necessarily find this kind of symmetric structure. So these are the things to observe in these solutions, and it is instructive once to check out this, and that will give you this kind of structures are extremely important in chemistry, because that tells you the shape of a molecule or shape of an atom, and this will tell you if that thing goes in a reaction and what part is, like some geometric configuration will matter, and then it will tell you what kind of reactions are more probable and all those things. So I'll give you a little discussion on this kind of thing, like how you go to the periodic table and look at the elements, and almost the entire chemistry can be worked out from here in principle. But of course it will get more and more difficult when there will be many electrons involved, and that is where all these 90% of modern chemistry, theoretical chemistry work is basically to use various fancy approximation and solve this wave function for a many electron problem, various kind of approximations. And then it there is something called Hartree-Fock, and there are this Born approximation and all those things. But the core problem is this problem, which you can solve exactly. And then a little bit, as soon as you start going to a little bit of deviation, even 2 electron like a helium atom, it's a notoriously difficult problem. And then you can imagine it's a multi-electron or some bigger molecule, it's already, it will get very difficult. But the entire chemistry, theoretical chemistry and physical chemistry, is basically one of the primary tasks is to solve this wave function for various difficult scenarios. And we will see some of these examples later, and we will discuss some it qualitatively a little bit later, means quantum mechanics too, and discuss it qualitatively in some cases. Okay, so now let me plot this wave function and the structures once, and just to see that what is the level of degeneracy and how many states are there corresponding to each energy level. So for n equal to 1, of course I can see the only allowed values are L equal to 0, M equal to 0. So there is total just one state. For n equal to 2, the L can be 0 and 1, because the only thing matters is this total n being equal. So sorry, the total n is this, so that is basically n plus L plus 1. So this capital N is basically telling me, so if I fix the n, so yeah, so this capital L is fixed here. Similarly, if I fix this n, so this L can be only 0 and 1 because there is this 1 here, and this in this case the capital N is here 1, and this is the capital N is here. What did it do? Yeah, both cases capital N is 1. Okay, so and so on. So you can do this solution. So for each of these cases, you know what are the m's. The m can be the m must satisfy this constant, that m is less equal to L, which we have seen earlier. So this case it will be 0, this 1 it will be -1 0 plus 1. So that is total 4 states. Similarly for 3 it is 0 1 and 2. This 0 will give you only one solution, this 1 will give you 3 solution, and 2 will give you 5 allowed solution. That's total of 9 states. So you can just count that how many states are there for a given n. So that is by just the sum of this 12 plus 1, all the possible values this L can take, and that is equal to n square. So second n equal to 2 will have 4 states, n equal to 3 will have 4 states. So if I plot these states here, so here I try to plot the state, and then I will see this form will emerge, that at n equal to so in this axis I am plotting the L, and this axis I am plotting the 1 by n square. So there is of course a unit, there is of course a unit which is this, so which I am not which I am ignoring for the time being, because I just want to give a structure of these levels. So everything will be multiplied by that z square, whatever unit I ignored. So if I plot the n equal to 0 solution, so all the solution which are there at the lowest point, so this is equal to n equal to 1 solution. So that is basically -1 in the 1 by n square scale. And then I can plot the n equal to 1 solution. So how many ways the n equal to 1 solution is possible in this case? So n equal to 1 solutions will give me a 0 L and 1 L. So n equal to, so this will give me this and this. So did I do something wrong? Yeah. So what did I do wrong here? L is 0, n is 1, L is 1, so I wrote it wrong here. Yeah. So these are the possible solution at here. So there are 2 states only possible. So n equal to 1 and n equal to 0, such that the total n is equal to 2. Similarly, if n is equal to 3, there are 3 states possible. So for one is so n equal to 3 is this. So at the same energy, you will get this n equal to 2, n equal to 1, and a total n equal to 0, which are at different L's, of course, because the only thing matters is to keep this, always remember this n plus L plus 1. This gives you the total energy. So this decides the total energy. So if I vary the L, I can vary the n also, and that will give me the same n. So that is that way you can construct, you can plot all these states. So these are like -1/9, this is -1 by 16, and so on. And you will notice that there are a lot of degeneracies here which you cannot really account with symmetries. So then if you see that these 2 states, they are completely 2 defined L orbitals. So if you plot even them, they don't have a symmetric relation. So let's look at this plot. So this plot is let's look at the plot of L at n equal to 2, L equal to 0 and 1. So let's look at this. Let's see how they look like. Where did that go? Yeah. So what are we looking at? We are looking at L equal to 0 and 1 for n equal to 2. L equal to 0 and L equal to 1. Yeah, so you can see here that these two has only one symmetry, which is the M symmetry. But even we are not accounting for the M. So even if I look at even M equal to 0 for both of these states, they don't look very symmetric. One has a perfect spherical symmetry, another has this on this axis, and this axis there is no symmetry. The only symmetry is along this axis. So similarly, you will find a lot of degeneracy which you cannot account for. So of course these degeneracies which is between these defined M states, that are accounted by the Z symmetry, by the symmetry around the Z axis. But even when you are finding a symmetry between the which are different M states, that you don't expect, because there is no geometric symmetry, there is no you cannot do a rotational operation and all, but there are still a lot of degeneracies. So these things are called, like as we discussed earlier also, these are called accidental degeneracies, and they are of similar type of degeneracy. So when we did this oscillator 2D oscillator problem, we saw that these states are symmetric. So 1 1 2 0 and 0 2. So these three states are symmetric. So these two can be accounted just by the symmetry of the problem, but this one cannot be accounted with the simple geometric symmetry of the problem. So this accidental degeneracy, but since there is the degeneracy, so one must think that there must be some hidden commutator relation or some hidden conserved quantity, and that leads to the discussion of it turns out that there is no very systematic way to find this hidden degeneracy, but for hydrogen atom one knows this thing. So this thing is called Runge-Lenz vector. So have you studied this thing in classical mechanics, the conserved quantity of Runge-Lenz vector in for hydrogen atom? Have you studied this quantity called N P cross, so not N, so N P cross L by M minus E square by R cap. Have you seen this quantity or anything like that? Am I connected? Am I connected? Can you hear me and see my screen? Am I connected?
Yes, sir.
At
Yes,
least?
sir.
Okay, good. Why there is so much silence? Did everything is totally unclear? Have you seen this Runge-Lenz vector? This should be a binary answer, right? Yes or no? Or maybe saw it but didn't realize what it is doing. Anything like that?
So we've seen this a bit in the first semester, like in our first semester, the central forces part. We had studied about LRL vector, so it's probably.
So, but this particular vector you have seen, that this is a symmetry of the problem. This is a conserved quantity. Just like momentum and angular momentum are N and L are conserved, P and L are conserved quantities. Similarly, this N is also a conserved quantity, but it is not so easy to see from the theory, like just from the geometry of the problem. Like if you just look at the problem of it is a rotating orbit problem or something, you cannot see this. It requires some special care, and that's why there is a special name associated with it by the people who found it. But have you seen this conserved quantity in this Coulomb or any central force, even gravity problem in Kepler law context or anything?
Yes, sir. We've seen the LRL vector in the first semester when we did like Kepler's stuff. But that's it. We haven't seen it for the Coulomb's case.
Okay, so but it is the same thing. It is there in any 1/r potential. If you have seen in gravity, it is also there in Coulomb potential because it's at the same structure. But the thing is that this is a symmetry of the problem, which is not obviously and easily visible, and normally one doesn't take into account. And this I will not go over the full detail of this problem, but what I'll do that I will give you an assignment problem to show that this N, from here you can construct an operator. Again, you elevate everything to be operator, and that guy commutes with the Hamiltonian. So that will give you another whole set of symmetry. So, and that symmetry will account for these relations, will account for these degeneracies. And similarly, for the for the harmonic oscillator problem, 2D harmonic oscillator problem, we found that there is a LZ, an LZ-like quantity, which is xpx minus xpy minus ypx. Similarly, we will so let me call it L3. I will show you that there are two L2 and L1, like two more quantities, which are like some weird combinations, which are not again easy to see. These can be worked out, which are not easy to see from the geometry of the problem, and that will again commute with the Hamiltonian, and this gives you like the so-called hidden symmetry, and will lead to this account for these accidental degeneracies. So the accidental degeneracies are not really accidental. They are just called accidental because they are initially people didn't see it, that where are they coming from, but then later because it is not easy to visualize, but one can find still these operators, which there is again no systematic way to find that, and it is possible that in some problem we will not find that. So among all the central force potential problem, this 1/r potential is a very special potential which has this symmetry, and that leads to this huge amount of degeneracy in this hydrogen atom problem. So that is all, basically that is all I had to say about this hydrogen atom problem. And maybe I'll put up a little bit of discussion in somewhere in the as pre-recorded or something, which I will not as an optional pre-recorded, it is not a compulsory part, to discuss about how it leads to a lot of understanding about the chemistry and periodic table. Like take elements from periodic table and see which have a hydrogen-like structure, which are almost analogous to hydrogen atom. And basically that is it. So that is all I wanted to discuss for today. So that's the class. If you have questions, we can discuss, or that's all.